Last month, NASA successfully completed the Artemis II mission by launching a spacecraft into orbit, then headed back for the moon, and then back through a re-entry process. There is a vast amount of math and physics that goes into these extremely complex and precise missions, from basic arithmetic to complex calculus.
The engineering and math that is required to make these missions successful comes directly from calculus. It's fascinating how scientists managed to send a spacecraft to the moon implemented integration and differentiation in the same way that we know how to.
Gravity plays a huge part in the way that motion is affected. In fact, the way that spacecrafts go about traveling throughout space is by slingshotting themselves forward with the help of a large mass's gravity. The swing by maneuver saves fuel and allows spacecrafts to effectively shift direction and speed. This concept revolves around orbital mechanics, the branch of math that focuses on how objects move under the influence of gravity.
Like satellites, Artemis II began its journey by entering Earth's orbit. When an object is in orbit, it's basically continuously falling towards the center, but it never hits the surface because the Earth curves away beneath it at the same rate the object falls. From there, Artemis II accelerated out of orbit, utilizing gravity to propel itself to the moon.
The spacecraft doesn't just fly in a straight path to the moon. It follows a unique curved path controlled by gravity and velocity. A mistake of just a fraction of a degree could send astronauts thousands of miles off course. The precision needed is incredible, which makes the Artemis II mission even more spectacular.
What's more is how scientists use parametrics and vectors in their work. Because we live in a 3D world, the normal Cartesian system doesn't apply. Orion is moving through a 3D space, so position can't just be modeled with x. It's a vector, r of t, with x and y and z components, each representing an individual function. NASA uses these vectors to get extremely accurate info on the exact position of spacecraft at any moment, as well as its future state. The vectors are always point relative to the center of the Earth, or the moon, or both at once.
The change in motion in the Artemis II mission can be represented as a vector differential equation. The second derivative of the position vector equals negative gm over magnitude of r cubed times r itself. One equation, yet three coupled components able to describe every orbit, every slingshot, every trajectory in the entire mission, and NASA did it by integrating numerically tiny step-by-steps, sort of like the Riemann sums. It's fascinating how simple math equations can get humans all the way to the moon, a place over 200,000 miles away. While rockets rely on large amounts of power and energy, a huge portion of that trip is completely reliant on math, physics, and gravity, so that the spacecraft follows the correct trajectory and returns back to Earth safely.
All the math that has developed over hundreds and thousands of years by people living in times way before rockets existed somehow culminated in playing a part in allowing humans to get to the moon.
Newton creating equations hundreds of years prior with no idea of the impact his discoveries would have ended up playing a significant role in our modern-day physics, math, and overall progression, and being one of the main reasons we understand how to get to the moon and travel thousands of miles away through space.
The way that Artemis II and the astronauts on board place all their trust on our fundamental grasps on gravity and motion is one of the reasons why space exploration is so beautiful. We humans are tiny specks of dust compared to the size of the universe, and the more we investigate, the more complex it gets. But even then, the cosmic language of mathematics is our way of explaining our curious existence, and it's a true testament to how far humanity has come.